Okay, thank you, Silvio, and thanks everyone for coming. So yeah, I did my bachelor thesis about this topic with Professor Imamoglu, and the topic of binary quadratic forms and the class group is quite a standard topic in algebraic number theory, and it's about an isomorphism between two groups, one of which is the class group, and the other group is something we will or I construct in my thesis. And the class group is quite an important number theoretic object, and this isomorphism then provides some kind of different way of looking at this group and some way to calculate certain things that would be quite difficult otherwise. Okay, so let's just start. Yeah, so as the title says, this thesis is about binary quadratic forms. Those are just functions of this form. And we look at integer inputs and also integer coefficients. So the output will always be an integer. The other thing is the class group, and maybe some of you don't really know what this is. So I will explain that to you in the course of this talk. But in any case, to understand the definition of the class group, we need to do some basic algebraic number theory first. So let's do this. But first, I want to give you a motivating example, which I find very cool personally. It's this theorem, first proven by Fermat, that says that a knot prime can be expressed as a sum of two squares if and only if it's congruent 1 mod 4. So the proof I'm going to show you is not by Fermat. It's I found only later because it uses some more advanced things that were discovered only later. So this is an if and only if statement, and so let's just start with the very easy direction. If a prime can be expressed as a sum of two squares, then it has to be congruent 1 mod 4. And why is that? Well, each square is either congruent to 0 or 1 mod 4. That's something which is very easy to check. And then the sum of two squares is 0, 1, or 2 mod 4, but certainly not 3. So the only case remaining if P is an odd prime is that it's 1 mod 4. Okay, and for the other direction, it's kind of trickier because we want to find two numbers such that P is the sum of the squares. And there's not really an obvious way how to find these numbers. But if you play around with the problem, you maybe get the idea to factor it in the complex numbers, and this might lead to the very useful observation that it suffices to show that in the ring of Gaussian integers, so this is just z adjoint I, the number P is not an irreducible element. So why is that? So if we can write P as the product of two non-units, then first of all, we can take the complex norm and square it. Then we get P squared on the left-hand side, and on the right-hand side, we get A squared plus B squared times C squared plus D squared. And now if we can show that non-units have complex norms strictly bigger than 1, we know that since this equation is in the integers, and both of these are greater than 1, then this implies that both of these integers have to be equal to P. So we get that P is equal to A squared plus B squared. So so we just have to verify that non-units have a norm greater than 1, and this can just be seen geometrically. I mean, this is all those lattice points are Gaussian integers. This is the unit disk, and the only places where the unit disk, the closed unit disk, intersects this lattice is in the 4 units and in 0, but that's certainly not one of those numbers. So that's how we derive that P is the sum of those two squares. So what we want to do is really we want to show that P is not an irreducible element in the Gaussian integers. All right, and maybe we know from algebra 1 that this ring here is a unique factorization domain. And in UFDs, we know that irreducible elements and prime elements are the same thing. So we can also show that P is not a prime in this ring. And what does this mean? Well, this just means we need to find two numbers such that P divides the product, but it doesn't divide either of those two numbers. And the way we construct these numbers is also a bit tricky, but it's doable, and we do it as follows. So first of all, we take a generator of the cyclic group of units in the field FP. So from algebra 2, we know that for each finite field, or the finite field FP, the group of units is actually cyclic. So there's a generator, and we take the generator U, and we just consider U to be an element in the integers. Then U has order P minus 1, and from this we get that P divides this thing here. And now, since P is odd, we can factor this because it's the difference of two squares. We get this. And again, we use that U has order P minus 1. So U to the P minus 1 divided by 2 is certainly not 1 mod P. And since P is a prime in Z, and this divisibility holds in Z, we know that P doesn't divide the left bracket. So P has to divide the right bracket. And now we make use of the fact that we assume P to be congruent 1 mod 4, and we factor this expression here in the Gaussian integers, and then we get this here. Okay, and now that's very close to what we want, because if P divides this product, but P doesn't divide either of these numbers, we're done. And in fact, it's quite easy to see that P doesn't divide both of these numbers, because if we write the product of P and some Gaussian integers, then we see that the real part and the imaginary part are both divisible by P. This is clearly not the case here. I mean, imaginary part here is minus 1, and the imaginary part here is 1. So we conclude that P is not a prime in Z adjoint I, and that finishes the proof that we can actually express P as a sum of two square numbers. Okay, so there was quite a lot going on here, but let's maybe learn something from this example. So what we did is we took a problem about the integers and we transformed it into a problem in the Gaussian integers, which is a bigger ring. Why the Gaussian integers? Yeah, because we could factor some expressions we couldn't factor in Z. And then we knew that Zi is a UFD, so we have some knowledge about the bigger ring, and this knowledge helped significantly to solve the problem in the bigger ring. And in the end, we just restrict ourselves, our view again, to the integers, and we conclude the solutions. And this is actually a common theme in algebraic number theory. So you have a problem, you want to treat your problem somewhere else where it's a bit easier. And if you know sufficiently enough about the domain where you extend your problem to, then you can solve the problem there and conclude about the solutions and see what's actually what you want. So this really motivates to study some ring extensions of Z. And in fact, it's not all rings behave equally well. So there's quite a unique construction of rings that lead to desirable results. So the general setting is we have a finite field extension K of Q, and then we define the ring of integers of K. We call it OK. And this is just consists of the elements of K that are roots of a monic polynomial with integer coefficients. So you might recognize this this thing as being an integral ring extension. And in fact, OK is integrally closed in its field of fractions K. And in any case, all you have to know here is just that this ring OK is the right choice. And it has many desirable properties, but it is not necessarily a unique factorization domain. That would be too nice. So yeah, there's already some quite small example where this is not UFD. But what we can say about this ring, this is very valuable, is that the ideals in this ring, they factor uniquely into prime ideals. So this really motivates to consider ideals in this ring instead of elements. And what you can ask yourself is now, how many non-principal ideals are in this ring? Because if all ideals were principal, then this ring would be a PID, and we know that PID implies UFD. But actually, for these rings, it's also the other way around. So if it were to be a UFD, then we would instantly know that it's a PID as well. So these two things go hand in hand. So the question about how many non-principal ideals of OK are there really is kind of equivalent to the question how much is this ring a UFD? And this motivates the definition of the following group. The ideal class group, which is just defined as a quotient group. And IK is a group of fractional ideals. And fractional ideals are just basically ideals of OK, but we're allowed to multiply some rational number to it as well. So you can divide your integral by some integer as well, your ideal. And PK is the group of principal fractional ideals. Those are just principal ideals, OK, with some constant. We need to consider fractional ideals here in order to have a group structure on the ideals. And then this quotient, so for example, if all ideals are principal, then this quotient is, of course, trivial. The class group is trivial, so this means the ring is a UFD. If the class group is very big, then the ring is quite far away from being UFD. So that's the heuristics. Okay, now let's look at what I did in my thesis. So in my thesis, the setting is quite a bit easier. We only look at quadratic field extensions, and we can express all quadratic field extensions as Q adjoint square root of D for some number D. And we can actually choose D to be square free, because if a square divides D, we can just take its root out and it doesn't change anything about the field extension. So we let D be a square free integer, and D is not equal to 1, because if it's 1, we just get K equal Q, and this is not interesting. All right. And the first step is we define two useful functions, trace and norm. And those can be defined generally using Galois conjugates. And in the quadratic case, there's really just one field automorphism that fixes Q, which takes square root D to minus square root D. So this is then the Galois conjugation. So for any element S in this field, we define the trace to be the sum of itself and its conjugate, and the norm is the product of S and its conjugate. So trace is an additive function, norm is a multiplicative function, and we can actually express trace and norm explicitly. All right, and one thing we notice is that an element is in the ring of integers if and only if its trace and its norm are rational integers. And this then helps us to characterize the rings of integers. So there's a theorem I proved in the thesis. So the ring of integer is always of the form Z adjoint an element, in the quadratic case at least. And this element depends on the residue of D modulo 4. Okay. So now we characterized the rings. We know how they look like. And OK is always a free Z module of rank 2. That's what the theorem tells us. And then it's not hard to show that every ideal of OK is the free Z module of rank 2 as well. So we can write I in this form here. And this leads to two definitions that kind of describe the size of an ideal. First is the ideal norm. So note that we also use n here, n of I. This will be justified in a case of the quotient ring, the ring of integers by the ideal. It kind of measures how widespread the ideal is. So the more widespread it is, the bigger we consider this ideal to be. And similarly, the discriminant of I is defined as this determinant here. And so there's a nice geometric interpretation of this quantity. So we can visualize the ring OK as a free Z module. We can visualize it as a lattice because it's a free Z module. So we can just like parameterize all points in OK by 2 integers. So we can view it as a lattice, and then each ideal is a sublattice. And then since the ideal is generated by alpha and beta, those are just two vectors in the sublattice. And then this determinant kind of describes the size of a fundamental parallelogram you can draw in this lattice. So both of these quantities describe the size of an ideal. And also what we can do, which is actually very important in algebraic number theory, is define the fundamental discriminant, which is just a discriminant of OK viewed as an ideal of itself. And we can explicitly compute that. It's not that hard because we also explicitly computed OK on the last slide. Yes, and these the fundamental discriminant of K, and it plays a central role in algebraic number theory. It contains information about what happens to primes in Z when we view them in OK. And what we can do is we can do some linear algebra to derive the following identity here that relates the discriminant and the norm of an ideal. So, and also this fundamental discriminant appears. Okay. So then after doing some more work, we can derive some quite useful properties of the ideal norm. For example, if we take the norm of a principal ideal generated by A, then we get the absolute value of the element norm of A. This kind of justifies the overloaded notation. And so actually we can just view each element as the ideal generated by itself. That's kind of what you do in those rings. Then the second identity, we can take an ideal and conjugate each element. And this is then again an ideal. And if we multiply, if we take the ideal product of I and its conjugate, we get a principal ideal generated by the norm of I. This is a very useful identity. And also what we get is if an element I is contained in an element J, then the norms divide each other. So the norm of the smaller element, note that if the set is bigger, then the ideal is considered to be smaller. So the norm of the smaller ideal divides the norm of the bigger one. And so finally, we can show that the ideal norm is even multiplicative. So it really satisfies a lot of the desirable properties for an ideal. And then it's really not hard to generalize everything to fractional ideals. So recall fractional ideal is just an ideal multiplied by some rational constant, and we can't just adapt the norm. So we take the rational constant out of the norm and multiply it somehow, and then we have a functioning concept of the norm of fractional ideals, which also satisfies all of these properties. And finally, we can show that the group of ideals, of fractional ideals, is indeed a group. So the group operation is just ideal multiplication. And the inverse can be seen by this formula here. So if we take the conjugate ideal and divide by an appropriate constant, we just get the whole ring. And the neutral element of this group is just the ring of integers OK itself. And we can also show that the positive principal fractional ideals are a subgroup of that group. And here we look at positive principal fractional ideals. That's different from the general setting from before. So this just means that they are generated by an element with positive norm. This is not always given. For example, if we have Q is equal to K is equal to Q adjoint square root 2, then the norm of square root 2 is minus 2. So it would be a negative. Would be a negative generator. Okay, and then we define the narrow class group as just this quotient here. And it's narrow because we only looked at the subgroup of positive principal fractional ideals. So the narrow ideal class group is generally bigger than the usual ideal class group. But in the quadratic case, they are very similar. They differ by a factor at most 2. Okay, then that's it about the ideal class group. So let's talk about binary quadratic forms. So all I did in my thesis is basically due to Gauss. So he really did a lot of work on this topic in his famous Disquisitiones. And so the ultimate goal in this chapter is we want to study binary quadratic forms. We want to figure out some things, and then we want to equip them with a group structure. So the goal of this is just to end up with a group. So let's just keep this in mind. So first of all, what we do is we abbreviate some things. Binary quadratic form is kind of long to always write down, so we just call it BQF. And also we can abbreviate each binary quadratic form as a triple because it's uniquely defined by the 3 constants A, B, and C. Okay, so from now on, we will always write binary quadratic form as a triple and only work with this notation. So one thing we can do is we can find a group action of the group SL2. So it is just a group of matrices with integer coefficients and determinant 1 on the set of binary quadratic forms. And so this looks maybe a bit confusing, but the idea is just we want to plug in some linear combinations of x and y. So here it would be alpha x plus beta y and gamma x plus delta y instead of x and y. And if we do that here, we would get some, just some terms in x squared, some terms in xy, and some terms in y squared. And if we group those terms again, then we would get some new coefficients, a prime, b prime, c prime. So we would get a binary quadratic form that looks kind of different, but is really the same thing, because all of these matrix transformations in SL2 are invertible. So we can just do the variable change, sort by coefficients, then do the inverse variable change, sort by coefficients, and we haven't changed anything. And that's the idea behind this group action. And we can even write the group action down explicitly, but it doesn't provide a lot of insight. It's just useful if you want to do some calculations. Yes, and as every group action does, sigma also defines an equivalence relation, which we just call tilde. And two elements are equivalent if there exists some matrix such that one element can be transformed into the other using the matrix. Or in other words, the orbits of sigma define the equivalence classes. Okay, so another important thing we note is that the discriminant of the binary quadratic form, b squared minus 4ac, is an invariant under this transformation. So here we also call this thing the discriminant. That's also not a coincidence. We will see later why those two things have the same name. So we can fix the discriminant and we can define the set BD. Those are just the forms with this particular discriminant D. And now since the discriminant is invariant under the action sigma, we can restrict the action to each of those sets BD, and then we can consider the equivalence classes inside or of the set BD. And then we can, first of all, exclude some boring values of D, because, for example, if D is a perfect square, then we see that the form, the binary quadratic form, splits into two linear factors. That's not very interesting. And the other way around also. So if it splits into linear factors, then D has to be a perfect square. So we exclude those values because they don't contribute to the theory of binary quadratic forms, really. And after we excluded that, we prove the following theorem, which is quite nice. So we can show that for any fixed discriminant, the set of equivalence classes is finite. So this is really cool because you can list all of the equivalence classes, and since we will construct our group using elements of these equivalence classes, we automatically know that the group is finite. And then if we show the correspondence to the class group, we also know that the class group is finite, which is actually a non-trivial result in algebraic number theory. Okay, so how do we prove that theorem? We want to show there's only a finite number of equivalence classes. So what we can do is we can just define a finite set of representatives such that each form can be reduced to one of these representatives. So we just construct some clever reduction algorithms and show that the algorithms terminate, and like the set they terminate in are finite. So here it's quite important to mention that the cases where D is positive and the cases where D is negative are very different from each other, in the sense that in the case that the discriminant is negative, we can describe all the classes pretty well by a finite set of representatives. So up to some small edge cases where two reduced forms can have the same class, we have almost a one-to-one correspondence between a reduced set and or a reduced set that can be described in a very easy way, and the classes here. But if D is positive, that's actually not very easy to achieve. So this is then something you can study on its own. It's a topic on its own, and it actually goes pretty deep. So you can show that some set of representatives have a very nice structure, but to prove the structure, you need to do some theory about continued fractions and about solutions of Pell equations and a lot of advanced stuff. So I didn't really treat this this theory in my thesis. I just made some remarks about it. But I did an example for d smaller than 0. Okay, so ultimately we want to arrive to a group. So we want to think about how we can define a composition on binary quadratic forms. And one idea that might be almost too obvious is, yeah, we can just multiply binary quadratic forms, right? But the problem is, I mean, you don't get quadratic things anymore. You get things of degree 4, but that can be omitted by just adjusting the variables a bit. So the question we can ask ourselves is, for any given binary quadratic form of the same discriminant, can we find a third form such that the product of the first two forms can be expressed as the third form in some crazy variables that are just linear combination, fixed linear combinations of pairwise products of x1, y1 and x2, y2. So yeah, we want to find some matrix, and we want to find a form F such that if we define capital X and capital Y in this way, we always have this equality here. So one easy example for this would be the following. If we have the product of sums of squares, then we can express this again as sums of squares in just these variables here, or these combinations. And there's an answer to this question found by Gauss. Gauss says, yes, it is always possible. Yes, as long as this d is always the same, we can find this. But as you can see, I mean, there are 8 variables already here, and we also have 3 constants for this f1 and 3 constants for this f2, and then we have to find 3 constants for this capital F. It could get really complicated. And besides, there's another thing that makes it more complicated, namely, this capital F is not really unique. You can find different matrices and different Fs that also work. But what Gauss figured out is that the equivalence class of F, capital F, is actually unique. So let's maybe have a quick look how Gauss did it. It's not pretty. So he does a lot of calculations. He does some more calculations, so at least 23 equations. He puts them together in lots of ways. But okay, if it's only 23, it's fine. No, it's not only 23. He also has some equations that don't even have a number. And yeah, but as long as he writes down everything nicely, it's fine, right? Yeah, but he writes the calculation is too big, so it's an exercise to the reader. Yeah, typical Gauss. So it's not really astonishing that people tried to find an easier way to approach this sense of composition. And what I did in my thesis is I followed an approach which was originally established by Dirichlet, who is one of the most important contributors to number theory. And Dirichlet's idea makes things much easier, but it's still not really easy. So you have to work a lot in order to get to the composition law. But the ideas are as follows. So first of all, we restrict some values of d. So we want d to be equal to the discriminant of some number field. So discriminant of the ring of integers for some quadratic extension k. Yeah, that restricts the possibilities. First of all, this is what we want to do in the thesis anyway, so it doesn't really hurt. And second of all, it allows us to figure some things out about the GCD of A, B, and C. So the GCD of A, B, and C will always be 1 if this choice of discriminant is made. And then what Dirichlet does is he determines some pairs of binary quadratic forms that have an easier composition law. So where it's actually easier to explicitly write down what the composition of these two forms is. And so then we can define some kind of preliminary composition on these good pairs. So this is not really a group composition in any sense. It's just like we take two forms and construct a third one without saying anything else. And of course, to be able to generalize this, we have to show somehow, like ultimately we want to generalize it to classes of binary quadratic forms. So we want to be able to show that for any two classes, we can find such a good pair. And if we prove that, we can generalize everything to the classes. And since we're always dealing with equivalence classes, well-definedness is always an issue that we have to solve. So I think I proved well-definedness about 10 times in the thesis. Yeah, because you always have to switch back between elements and classes. Yeah. Okay, and then you can actually show that now this extended composition on the classes defines a group composition, and we can also then restrict this group further to the group we actually want. So we define the class group of binary quadratic forms. It's just exactly this group if the discriminant is positive. But if the discriminant is negative, then we get some positive definite forms and some negative definite forms, and we only want the positive definite ones. This is not a big restriction because every negative definite form is just positive definite form where everything is multiplied by -1. So there's no additional information about negative definite forms anyway. And for the correspondence theorem, this really only works well if we take positive definite forms. Okay, and so I explained how to derive this group, but it's not at all clear what this group is now. I just said, yeah, we do some composition and then we do this and that, but what this group looks like is still a mystery. So I quickly want to tell you how the composition law actually works. So we want to take two forms here, or two classes of forms. And we can actually impose that the GCD of A1 and A2 is equal to 1. This corresponds to the property of being a good pair, as mentioned earlier. And so, yeah, we want to compute the composition of those two classes. And what we have to do is first we have to find some integers p and q such that these two equivalences here hold. This is doable. And once we found such p and q, they are not unique, by the way, we can define the composition as this class here. And what I also did in my thesis is then I showed that this is really the composition in the sense of Gauss. So we can construct this matrix such that this form evaluated at some linear combinations of the variables is equal to the product of those two forms. Okay, so but what's the unit element or the identity element of the group? This can be written down like this. Depends on the congruence of D mod 4. And here we only have to look at 0 or 1 mod 4. And this is just due to the fact that we assumed capital D to be a discriminant of a number field. And we computed the discriminant of a quadratic number field before. And it turns out that only 0 or 1 are possible. So we have these two identity elements, or the identity element in these two cases. And what's the inverse? The inverse is actually, I think, the easiest to memorize. It's just, we just flip around the form, or we exchange A and C. Then we get the inverse class. Okay, so yeah, this group is not really easy to define, but there are algorithmic ways to compute in this group. So it is of use if you want to study the class group and already know that these two groups are isomorphic, then this group can be useful. Okay, so now in the third chapter of my thesis, I finally proved the correspondence theorem. So this just says that those two groups here are isomorphic. So this group here is the narrow class group of ideals, and this here is the class group of binary quadratic forms. And D and K are related via this equation here. So K is K can also be written as Q adjoint square root of capital D. Okay, so how do we do this? So the basic observation that leads to this isomorphism in the end is that so if we have, oh sorry, I didn't mention that. So if we have an ideal that is generated by alpha and beta, then we can parameterize every element of this ideal by x alpha plus y beta for some integers x and y. And if we take the norm of this fractional ideal, then the expression we get is actually almost a binary quadratic form in the variables x and y. So it is exactly a binary quadratic form if the ideal is a proper ideal. But if it's a fractional ideal, we might have some constants we have to deal with. So, and what we have to consider is that if we exchange the role of alpha and beta, we get a different expression for the norm, or a different quadratic form. And this is why we have to define or work with ordered bases. So the first step is to define a set of ordered bases, and this is just an arbitrary choice. And then we define this function here. So we take an ordered base alpha beta to this binary quadratic form, and the fact that these two or these three constants here are in fact integers, this follows from the work we did in the first chapter. So we have, and we for sure we have to prove well-definedness. So we have to prove that this binary quadratic form really has discriminant D. But this is not too hard to do. Then the next thing we show is that if we take a different basis for the same ideal or the same fractional ideal, we end up with the same class of binary quadratic forms. And this then allows us to extend the map phi to a group homomorphism, which we call capital phi. This goes from the fractional ideals to the class group, narrow class group of ideals. Oh, this is a mistake. It should be CD, not CK. I'm sorry. So this goes to the class group of binary quadratic forms. So it should be a CD here. Terribly sorry for that. I will change that later. All right, and so two things. First of all, we really only get positive definite forms here in the case D smaller or equal than 0, because in this case the norm is always positive. And secondly, we can show that this is in fact a group homomorphism, and we can even show that it is surjective. And also we can compute the kernel of the group homomorphism, and this will just be the subgroup of positive principal fractional ideals. Okay, and then we are actually almost done because we can just apply the first isomorphism theorem, and we get that this quotient here, ik quotient pk plus, is isomorphic to CD. Okay, so let's summarize this again in a diagram. So on the left-hand side, we have the theory of ideals in number fields. On the right-hand side, we have binary quadratic forms. So we have a group action sigma of this group here to the set of binary quadratic forms of discriminant D. And then we can, using this group action, we can kind of project everything down to this group CD. And similarly, we can define the ordered basis. And here we also have a group action because base changes of ordered basis exactly correspond to matrices in SL2 of C. So we have these two group actions. They are kind of symmetric, or they're kind of equivalent to each other. And we have this map phi we defined in the thesis. And also we can just project every ordered basis onto the ideal it generates. And here we have a group again. And then this map here becomes a group homomorphism. And here we show its surjective. And then by the first isomorphism theorem, we have this quotient group here is isomorphic to the image. So this whole diagram is commutative. So yeah, that was my thesis in a nutshell. I want to thank you a lot for listening and for attending.